Alright guys, we're going to go back into everything and go on to a new chapter now that we're done with circular motion. And the chapter 6, which we're beginning, is going to be on work and kinetic energy. And at some point today you're going to really learn that work really comes back to understanding forces and Newton's laws, just maybe in a different aspect of it, but it still all really comes from Newton's laws, which we'll show eventually. Alright, so I'm going to use a simulation that you guys are somewhat familiar with. When we did an incline one, we had something that kind of looked like this thing. And all we have is an object, a crate in this case, with whatever weight, balancing with its normal force because we're on a flat surface and no pushes or pulls on it yet. But our goal is to define work today in section 6.1 and make sure we're really clear on when work is done and when it isn't done. And it's not that hard of a concept, but there sometimes are some tricky scenarios we need to watch out for. Okay, so number one, something that has to be true in order for work to be done on an object is that there's got to be displacement of that object. All right. If something is not moving, we could absolutely guarantee that no work is being done on it by any force. All right. So the number one thing is displacement. So like if I took this person and put an applied force on this object, even though I'm applying a force on this object, on this crate, this person has done no work on it in the eyes of physics, on the crate. Now you might say, well, boy, if that person sits there for a long time and pushes on something heavy, they're going to get tired, right? They've got to do work if they get tired. Well, it's all in how we asked it. I said that the person did not do work on the crate. You could take work in different aspects of a level, like a muscular level of the person. When a person applies a force on something, your muscles contract and move, and there's all kind of stuff inside your body going on that might have moved, and stretched your muscles. And yes, you did work on your muscles and you got tired from that, but that's not the question. What the question was, is if I push on this crate and apply a force to it, do I do work on that crate? And the answer is no, absolutely not, because the crate did not move. So you have to have displacement to do work on something. As a matter of fact, the two key components of work on an object is that object displaces and there is a force that caused the displacement or is causing the displacement currently. All right. Some forces that are present here, even when I do push it hard enough, now that I'm in contact with it still, I'm doing work on it. But normal force and weight, they're there, right? Their forces are there, but they're forces that are not on the axis of the displacement. So normal force and gravity in this condition, in this scenario, are not doing any work on that object. If those forces had any bit of a component on the axis of the displacement, they would be involved in doing work, but they don't. When I do start to push this, since it's not friction-free, friction is on the axis of the work. We'll talk about that more later. So it's also providing some work. If this person pushes it and lets go, the person was no longer in contact with that block when I push and let go. And therefore friction is the only thing doing work on it then. All right, so there might be only one force doing work. There could be multiple forces doing work. But the forces do not do work unless they are on the axis of the displacement, causing the displacement. Okay, so that's all like the general characteristics of this work is being done or not. But let me take some other situations that I can't show on that simulation, so I'll just use myself here. All right. Normally, if we were all together, you would watch me walk across the room with this, but my camera won't go that far, so I'm just going to walk a few steps. notice where my hands are. They're under the book, right? So I'm going to walk at a constant speed for a moment. I can't do it very long. I'll walk back towards the camera. It is at a fairly constant speed. Then I'll stop. Okay, while I was moving at that constant speed, another question is, did I do work on that book? And you might jump to say, from what we just discussed, well, he was obviously putting a force on the book, and the book was moving and displacing, right, its position. So yes, but careful. The answer is no. All right. I asked if I did work on the book. First of all, where are my hands when I was carrying it, whether it was towards or away from the camera? My hands are underneath the book. And that means my only force, walking like this, my force is upward. And any displacement was on this axis. So there's one reason why I did not do any work on this book. My force was not on the axis of displacement, not even part of it was. No component of my force was. And the majority of my trip, I told you I was walking at a constant speed. Now we'll get to the beginning and end of the trip in a second. But as I walk with constant speed, no force is doing work on this. You might say, well, friction's there, all right? But this is where Newton's first law comes back in. If this book is traveling at constant speed, in the nature of the fashion I was holding it, remember what Newton's first law says, part of what it says. Objects moving at constant velocity maintain that constant velocity unless acted upon by an unbalanced force, right? Or in other words, things want to keep doing what they're doing, inertia, right? So this book, once it is moving at constant velocity, wants to keep doing that. And if there's no significant resistance, you could say there's air resistance in this room, yes. But if I'm walking and take my hands away, I'm just going to kind of help the book down so it doesn't fully drop. If I take my hands away, it will keep going forward the direction I was walking in until gravity takes it down and makes it stop. But theoretically, if I could have a gravity switch and shut it off, all right, and took my hands out from under this book while I was walking, wouldn't it continue to move at whatever constant speed I was moving at? Therefore, if it would continue to move at that rate anyway, displaced on the x-axis that way anyways, no forces were needed to continue its motion. So let's go revisit something I said to start with work. I said we could guarantee that if something is not moving, there's definitely no work on it. However, you got to be careful now, especially with this example. If there is motion, that doesn't guarantee it either, but there's a good chance of it. But if something would continue to keep moving the way it was, Newton's first law, inertia, without any of the forces present, then those forces weren't doing work on it. That's where you got to be careful for some scenarios. Okay? But now let's go back to, of course, something can't get into constant speed just magically, right? So there had to be a time I started walking and got this book into motion and caused it to accelerate to some constant speed as I walked at it, right? And there was work done during that moment, okay, for it to accelerate from rest to a constant speed. But still, that work was not done by my force, because my force is upward. But there is friction between the book and my hands. And to accelerate this up to a constant speed, there is static friction, because it's not sliding in my hands, between me and the book, that did do work on it then. But remember, once I went constant, even though that my hands are touching the book, that if it wants to keep moving on its own, even without my hands and that friction there, then that's not doing work anymore. But then I come to a stop. A stop is another form of acceleration, right? Friction does work there again. Not me, not my force, because my force is still upward. All right? So the main things, yes, there has to be displacement, but there has to be forces that are causing that displacement. It wouldn't just do it all on its own due to inertia. They have to be present. And there's more mathematically, we'll get into that. We'll just come back and revisit Newton's first law and second law as well, really, when discussing that. All right, back to, in a second here, okay. Try to get back to my other screen. Okay, here we go. Back to just some other general ideas before we jump in some problems about work. Let me hit the notes here for us. This whole chapter is titled Work and Kinetic Energy, and as we go through it, we'll see they go hand in hand. All right. Kinetic energy is defined as the energy of motion. And as a formula, it's Ke equals 1/2 mv squared. We'll worry about that more later. But when you do work on an object, you change that object's kinetic energy. So they're related in that fashion, and we'll expand on that as we go through this chapter. And while all that's happening, we got to keep in mind is something you may have heard of before in like a more general science, the law of conservation of energy. In other words, energy cannot be created or destroyed. It can be converted from one form to another, though. All right, so you can't just magically make up or amount of energy or have it disappear. It transfers from one form to the other through a variety of processes because there's many different forms of energy. And we get introduced to energy in this chapter and spend some others expanding on our ideas of energy in the future. So, to define work, which is when a force causes displacement of an object, right? Through kinetic energy, we say the total work done on a particle or an object by all forces that act on it equals its change in kinetic energy. So if we gather all the work that we applied to something, that same amount of work, if we calculate it, happens to also equal the change in kinetic energy that work caused. And that means work and energy basically go hand in hand. Work and kinetic energy especially, but some other types as well. We'll expand into potential energy next chapter. But since they're kind of really the same thing, if the total amount of work equals the change in kinetic energy, then they must have the same unit, which they do. You might know from chem classes studying stuff with energy that energy is measured in joules. And a joule is a Newton meter, okay? It's renamed. Joule is the last name of some guy that studied this. And 1 Newton meter is a joule. And joules are a valid unit for work, or the core metric unit, I should say, for work and kinetic energy. And just as an idea, 1 joule of energy or work is not that much. So we will often get, for any significant amount of work done, get fairly large numbers in joules, which is why sometimes we put it in kilojoules, you'll see, because of the large numbers. All right, so let's get more formula related now that we know the concepts of this stuff. All right, so the formula, the base formula for work is simply the force times the displacement. And trying to scroll to find something here. And when using this formula, a couple key things here. One, displacement, your textbook, when applied to work, uses S as displacement. You could use D if you want. I don't really care, okay? But I'm going to go along with what your textbook does here. So this formula of straight up multiplying F times S, though, we got to be careful with, because that is only true if the force is on the axis of the displacement. That we could just do a simple multiplication of them. But for now, for the moment, if that's the case, if we multiply the force in newtons and displacement, we typically want as a core unit of meters, right, in the metric system, we get Newton meters. And that's what I said a moment ago, 1 joule is equal to. So both work and energy not just kinetic energy, all forms of energy, we use joules as the core common unit in the metric system. Just as a FYI, Newton meter, which again is a joule, its English equivalent is foot-pounds. And we might bring that up again later when we get to torque. And like I mentioned also, 1 joule is a very small amount of work. And using this form of just F times F is only good if that force is along the same axis as our displacement vector S. So I broke down some scenarios here to show us what we have to do if it's not. Alright, so simply put, scenario A, we apply a force and it moves some displacement. I have a motion arrow down here, just doesn't mean it's definitely moving. And its motion is caused by force F. You could see that that force is on the same axis as the displacement, and I simply multiply the two. However, we all know by now, many forces could be at angles to the motion. And we've studied this when we did Newton's law stuff. When we pull at an angle, we have 2 components of F. The horizontal component, which could be found by F cosine of the angle, which I define as phi in this picture, and the vertical component of the force. But the vertical component of the force is not causing motion vertically. So the vertical component of this force, force F, is not considered when doing work. So we only use the component that's along the axis of displacement, which is the horizontal component, which is F cosine phi. So to find out the work that this force did at an angle, if this is all the case, then we would use F times S cosine of the theta, which isolates only the piece of the force causing displacement and affecting displacement. And a better catch-all formula, since that is the case when forces are angles to displacement, goes back to something we learned about in our generic vector math chapter that started the year. So usually, because of what we described, we give the work formula as a dot product. F dot S. You might recall that when we gave generic dot products to learn about them earlier in the year, we gave it as just vectors A and vector B. A dot B was AB cosine theta, right? That's recalling from chapter 1. Well, F dot S, the dot or scalar product as it was also called, is Fs times the cosine of the angle. And notice that exactly corresponds to what we got here that isolates the component of the force that is doing work and ignoring the component which is not causing displacement. But this still works even with the cosine theta on this simple thing. If you don't consider it, still works out. But what's the angle between the force and displacement in diagram A right here? Well, they're pointing in the same direction, so 0. But the cosine of 0 is 1. Therefore, 1 times the magnitude F times the magnitude S is just Fs, right? So this is the catch-all formula that considers everything. Writing it as a dot product is really the best way to go. And I want to throw out a reminder, there was a secondary way to find the dot or scalar product that we learned a while ago, and that doesn't use the angle directly. And it was if you had the components, or maybe you were given unit vector notation that gave you components of the vectors involved. Generically, if it's vector A and B, we had a secondary formula that said x component of A times the x component of B plus the y component of A times the y component of B. Total that all up, and that would give you the dot product as well. If we just applied it for the specific variables in this formula instead of A and B, F and S, we would do the similar thing using their components. And again, don't forget that the dot product is also known as, aka, the scalar product. So that must mean our answer is a scalar quantity. And this we have to discuss closely before we jump into any examples as well. Because wait a second, force is a vector. Scalar is a force is a vector. Displacement, S, is a vector. But yet when we calculate their work through this formula, through the dot product in any fashion, our answer is a scalar product. The ideas of work and energy are scalars. And that may sound weird, but especially with work, they come from magnitudes of vectors. We might consider the directions independently of those vectors, F and S, at some point. But when calculating the dot product between them to find work, it is a scalar quantity. And that leads us to something that will happen to you. We can get out negative amounts of work. Wait a second, I just sound like I contradicted myself, right? But we've been used to positive and negative representing directions in a 1D axis, right? If we have motion on this axis, we often said positives to the right, negatives to the left. Well, positive and negative have a whole different meaning as applied to work and energy. They don't represent direction, so they therefore can be used even on a scalar product like we're applying here. Why? Because you could think of, if you get a positive amount of work out when you calculate it, that means a net gain of work to the system, to the object in the system we're defining that work placed on. Okay? If we get out a negative amount of work, then that means we get out a loss of energy from the system. So it's not technically direction anymore. Even though when you apply it just solely to the forces and displacements interacting, you could still count it as directions. But when we tie it into work, a positive work's a net gain of work or energy on the system. A negative amount of work is a loss of energy from the system, taken away from it. We'll, again, expand on that more soon. Okay? But now we hopefully at least know enough to do a basic example of work. So we're going to go to your textbooks, example 6.1 on page 174. You should have your textbooks open with me so you can see the wording of the problem. It says in part A, or for the whole thing, work done by a constant force. Steve exerts a steady force of magnitude 210 newtons, which is about 47 pounds, on a stalled car in figure 6.3 above. I have a rough diagram of it right here. He pushes at a distance of 18 meters. The car also has a flat tire, so to make the car track straight, Steve must push at an angle of 30 degrees to the direction of the motion. How much work does Steve do is the first thing we're asked. So we know Steve applies a force of 210 newtons. And it displaces the car 18 meters. But a key thing is that the force is at an angle to the displacement, given angle of 30 degrees. So we cannot just simply say work equals F times S, because not all of his force is in the direction of, on the axis of the displacement. That's why we explained a minute ago the best way to define this is through the dot product, because the dot product of these two vectors is Fs cosine theta, which in turns just isolates the horizontal component of the force that is along that and ignores the vertical piece of the force that is not on that axis, okay, in our diagram. So all we have to do is simply consider that. We place 210 in, forces in newtons, that's what we want. Displacement in meters, 18 times the cosine of the angle, and we get out 3,300 joules of work that Steve applies to this vehicle. Part B. In a helpful mood, Steve pushes a second stalled car with a steady force F equals, we were given this in unit vector notation. Remember, just a quick review, unit vector notation, whatever comes before an I hat is a horizontal component. Whatever comes after a J hat is a vertical component. The displacement of the car is also given in unit vector notation. So this displacement is not on a single axis either. The displacement has some displacement on the horizontal x-axis because there's an I hat there, and on the vertical y-axis because there's a j hat there. We do not know the angle, but as I said and reviewed up here, remember the secondary formula. If we have all the components of F and displacement, we could use that formula if necessary without the angle to figure out the work. And when we do, it's just the x component of F times the x component of the displacement added to the y component of F plus the y component, or times the y component, excuse me, of S. And this is a scalar product, right? That means when you go through it, there's no more I hat and j hat. Direction's not considered anymore. So we do a straight up total of these values once we do the multiplication of the components. So adding that all together, though, this plus that, comes out to Steve doing 1,800 joules of work on this vehicle. So that's about as simple as a work problem as you're going to get. Just understand how we use this formula, right? Again, if this force was in the same direction as S, we could just multiply them or consider the angle, excuse me, 0 degrees, and cosine of 0 is 1, which is F times S anyway. All right, so a little bit more now after a basic example of work being positive, negative, or 0. As I already mentioned a moment ago, those will not represent, positive and negatives, will not represent direction of work, but if work or energy was put into the system as opposed to taken out of the system if it's negative. And the 0 part, kind of mentioned this before, but I'll be a little more clear now. If a force is perpendicular to displacement, the work is 0. I could prove that mathematically by the fact of us using the dot product. All right? Remember, the angle of formula for the dot product is Fs cosine theta. So if I have a force perpendicular to the displacement, if I have a force on the y-axis and the displacement is on the x-axis, I mentioned this earlier with this. So I am doing work on this, and so is friction once it starts moving. But normal force and weight are on the perpendicular axis. They do no work. In concept and even mathematically, we could prove that. Because perpendicular is 90 degrees. Cosine of 90 is 0. So if we plug that into the formula, it doesn't matter what the force of like gravity is, because it does not act on that axis. Therefore, the displacement is not caused by it, making this whole idea 0. So never does a force do work when it's on something when it's perpendicular to the displacement. Just a small list of scenarios when work is 0 here. Pushing on a wall. You don't do any work on that wall if it doesn't move. Holding up even something heavy like a barbell. Holding it. All right? Not moving it, just holding it there still. You might get tired, but you're not doing any work on that barbell. Another one, we already discussed your hands on the book when carrying it. I already went over that example, why there would work with 0 there. But centripetal force during uniform circular motion, that might sound surprising. We just did circular motion. When we're whirling something in a circle, quick small little diagram hopefully you can make out here. Remember, the centripetal force is always towards the center. So let's imagine again an object on a string whirling around. So the centripetal force is tension. Let's just say this is a horizontal circle, whirling around with a tension. The motion at any given moment, the velocity is tangent, remember? And tangent is defined as perpendicular from the radius to the center of the circle at any given moment. So based on this definition up here, if the force is perpendicular to displacement, the work by it's 0. All right, so the centripetal force is always perpendicular to the motion when something's moving in a circle, therefore not doing any work on it. And the meaning of negative work, I already kind of went into that some, but I have marked here to look at a figure 6.6 on page 176 to further explain this a little bit more. You see somebody lifting a barbell. Well, I don't have a barbell, so this empty bottle of water is going to be my barbell. Okay? When I lower it to the floor, like in diagram A, I'm lowering it, but my force is still upward, right? If I'm holding it like this, my force is upward, lowering it down. But now my displacement in a situation like this is on the vertical axis. Let me make my screen a little bit bigger while describing this. So, think free body diagram at any given moment. My force is always up even when lowering it. Where's gravity? Always down. In this case, gravity is doing work. Why? Because it's on the axis of displacement now. So as I lower it, two things are doing work. Me and gravity. So whatever force I'm applying on it, I'm doing negative work. Wait a second. Why? Because my force is upward. Where's the displacement? Downward. And this is a very important idea. When the force is completely in the opposite direction on the axis of displacement, it does negative work on the object. Negative work. And remember, negative work really, in the end though, is taking energy out of the system. All right? I know I kind of described that there with some directional stuff, but once we get a number for it and say it's negative, I don't know, negative 100 joules is what my hand's doing, then that means I took energy out of the system. Now, how did I take energy out of the system? Well, what else is doing work on it? Gravity, right? What does gravity really want it to do? Fall. My hand's getting in the way by lowering it down, right? So gravity, force of gravity is just the weight, but gravity is in the same direction as the displacement when I lower it. So the angle between them is 0. So Fs times the cosine of 0, the magnitude of the force of gravity, times the magnitude of the displacement, is what the cross product, or dot product, excuse me, tells us to do in the formula. And if they're pointing in the same direction, that's cosine 0. So gravity is doing positive work on this as it falls, or even as I lower it. Because if the force is in the direction, the same direction of the displacement, then that's positive work. My force, though, is going against gravity. I'm taking energy out of the system that wants to be there. All right? This thing wants to just fall. I'm not letting it. I'm resisting it. So I'm doing a negative amount of work on it. But another way you could think about it is my force is this way, displacement is this way. So that means the angle between those two vectors is 180 degrees. What's the cosine of 180? -1. So when I take my force, whatever that is, and multiply it by the magnitude of the displacement, the magnitude of my force times the magnitude of the displacement, times the cosine of 180, because they're completely opposite, on the same axis but opposite in direction, I get a negative amount of work. All right? I'm resisting against gravity, which is doing a positive amount of work there. All right, we already said, though, let's go to diagram B of these 6.6 on page 176. When I lift up on it, I'm sorry, that actually looks like diagram C. Whatever the diagram it is there, when I push up on it, now I'm doing positive work. Because now the displacement is upward and my force is in the same direction. The angle between them is 0. When I'm pushing it upward, now it's gravity doing the negative work. Right? Gravity is doing the negative work now because displacement's up, gravity's down. Cosine 180 is -1. All right, so that's how we figure if work should be positive or negative. If the force, or component of the force at least, if it's at an angle, is in the same direction as the displacement, that's positive work. If those are in the opposite directions, then it's negative work. And as I mentioned several times throughout some examples, many times there are multiple forces doing work on something. So we might have to figure out the total work. So again, back to either lifting or lowering this bottle or any object like this. Both me and gravity are doing some amounts of work. So if I want the total work, we could find each force separately, then sum it all up. Or we could use the net force and take it times the displacement as well. We know what net force means from the past in working with Newton's laws. All right, and we'll see some of this done through examples. So let's now go to example 6.2 on page 176. It says a farmer hitches her tractor to a sled loaded with firewood and pulls at a distance of 20 meters along level ground. The total weight of the sled and the load is 14,700 newtons. The tractor exerts a constant 5,000 newton force at an angle of 36.9 degrees above the horizontal. A 3,500 newton frictional force opposes the sled's motion. Find the work done by each force on the sled, acting on the sled, and the total work done by all the forces. Okay, so my free body diagram of what's going on here shows this is the tension force that the tractor is pulling with on this chain that it's hooked to. It's at an angle. Normal force on this axis, weight on this axis, and frictional force to the left. I know it looks like I have two arrows down here. Not sure why. There's only one force down, and that's the weight of the wood here. And we know it displaces, let's say to the right, at 20 meters. So no work is done on this axis by normal or gravity force because they're perpendicular. Cosine 90 is 0. No work being done on that axis. It's not contributing to any work done. So we want the work, the tension that's hooked onto the tractor, WT, is doing. We want to find them individual work first. So it is at an angle, so we got to use Fs cosine of the angle to find the work it's doing. But the horizontal component of Ft is in the direction of the displacement 20 meters to the right. So it's positive work. It's a cosine of the angle between them pointing in the same direction. So the tractor is doing positive work because its horizontal component, isolated by cosine of 36.9, is in the same direction as the displacement 20 meters along the horizontal. And it's 80,000 joules, but like I said earlier, if it's big numbers, we might put it in kilojoules. You only have to if asked. Okay, so 80,000 kilojoules. Now, there's another force on the same axis as the displacement, that's friction. But friction is completely opposite of it, which means it's going to do negative work. Now, you got one or two options for making it negative. A, you either just realize it and slap on the negative like I do here, or you can claim that it's cosine of 180, because the displacement is this way on this axis, and the frictional force is completely opposite. The angle between them is 180. Cosine of 180 is -1, making whatever the amount of work is negative. I don't care how you figure it out, just realize that it's negative because the force doing the work is 100% opposite. So on the same axis, but 100% opposite direction as a displacement. That's how we calculate and consider negative work. So the work of friction is -70 kilojoules or -70,000 joules. Friction always takes work out of, or work and energy out of the system. All right, which is why it's negative. We lose that energy. All right, it goes out of the system, and in terms of friction, we'll learn at a later time that friction is a non-conservative force, and when you lose energy due to it out of the system, you really can't get it back. At least not easily. But anyways, tractor does 80,000 kilojoules of positive work, puts on the sled, puts energy into the sled. That's what that means. Friction takes energy out of the sled system sliding along the floor. And the total as asked is 10 kilojoules. So we found the total work in this example by finding all the individual works and simply totaling them up. Easy, right? But another option we set up here was use the net force. So we could find the total work if we did the net force. It's still doing the same thing we did above, just maybe condensing it a little bit. It's the same idea. Well, the forces that exist are still the same. We find that do the work. We only want to sum up the forces that do the work, which we already identified as only the x component, the horizontal component of the tension, which was Ft cosine of the angle right there, minus the frictional force. Why? Because minus it, because doing net force, right's positive, left's negative. Right here I'm just doing sum of all forces on the x-axis, which we know how to do. So if I find the net force, I get 500 newtons. And if I multiply the net force, 500 newtons, times the displacement 20, I still get 10,000 joules or 10 kilojoules. So I guess you could say that finding total work through the top method here, finding the individual works and totaling them up, might be streamlined a little bit quicker by doing it by finding the net force and then taking the net force times that to find the total. Either one really doesn't matter how you do it unless a problem specifically asks to do it a certain way. Okay? Either one's a valid way to find the total work done. So tomorrow or later we'll get into kinetic energy's involvement a little bit more. But I think right now we got a good start of enough to think about out of this first section. And I am going to post with this a set of problems out of section 6.1 to begin.